Starting us off in chapter 3, we want to talk about counting units. Okay, so for chapter 3, we're going to start to move into talking about chemical reactions. It's really where we want to go. You know, we've talked about all the language as to how we would measure these things, describe things. We want to start talking about some chemistry. And so when we actually functionally be performing chemical reactions, you know, we'd measure out some different, say, elements. Say we could look at, we want to react some lead, we want to react some sulfur, and we're going to make lead to sulfide, right? So we're going to perform a chemical process. In order to do that, we need to measure out amounts of the different substances that are involved in this reaction. And so when we do that measuring out, we do it using grams, right? When we measure things out in, say, a lab setting, everything's always going to be in the grams measurement when we're using an actual balance. And so that's going to be our kind of unit that we're going to use to measure amounts. The thing is, reactions actually happen by atoms. So you may put some lead and some sulfur together and make some lead 2 sulfide. But what's really going to happen is that one of these lead atoms is going to react with one of these sulfur atoms, and you're going to make one formula unit of the lead 2 sulfide, right? It's going to be that reaction happens via a ratio based on a number of atoms, not on just some sort of amounts of mass. So when we're performing chemical reactions, we want a certain number of atoms. We want a certain number of atoms that we can use that we would be involved in this chemical process, okay? And so generally we're going to be dealing with large amounts of them, say 100,000 of each kind of atom. But at the same time, you can't use, there's no piece of equipment that measures an amount of atoms. You can only measure mass. So there's two main things that we want to address here. The first is we want to efficiently count atoms. It's going to be cumbersome to be talking about thousands or millions of atoms or something like that at a time. We want a way to efficiently count atoms, and we're going to need a way to convert between this number representation and the actual functional mass representation. So we're going to need a way to deal with that. So those are the two types of factors that we want to deal with, that this chapter 3, what we're going to work through, especially this first set of videos, so how to get through that idea. So the question of counting large groups efficiently is a solved problem. We use what are called counting units. And a counting unit is just basically a defined unit based on a number of objects. And so we use these counting unit representations as a way to just more efficiently count large groups. So some of these you're familiar with from everyday life, say for example, dozens. 1 dozen is 12 objects. So you could say have like a dozen rolls. Usually we use this for food type products. So if you, instead of saying 12, you could say 1 dozen, and you could have 3 dozen. And the idea is saying 36 rolls or 36 muffins is kind of hard to imagine what that is. But if you know what a dozen is, then 3 dozen is kind of a reasonable amount or an easier idea to wrap your head around. 1 gross is actually 12 dozens or 144 objects. So that'd be if you have a lot of them. So for example, if you have a lot of pencils, 1 gross is a useful object. A score is 20 objects, and a ream is 500 objects. So you may be familiar with a ream of paper. That's kind of the standard kind of package of paper. There are 500 sheets of paper in there. So like 3,000 pieces of paper seems like a lot of paper, but it's kind of hard to wrap your head around that because that's just a lot of small things put together. But a ream is kind of an object like, okay, that's a decent chunk of paper. You have an idea maybe as to how long it takes you to go through a ream, and so how many of that would be. It's hard to kind of count day to day how many pieces of paper you use. We can use these counting objects, we use, for example, 3,750 sheets of paper a week. That feels like a lot, right? That's a lot, that's a high number, but each piece of paper is really small. But if we use that in terms of a counting unit representation, 7.5 reams of paper a week, that kind of lets you kind of wrap your head around what kind of size that is, how much actual physical space that takes up, what kind of cost you'd be dealing with, those sorts of ideas. We need 126 donuts for the party. That seems like a lot, right? And it certainly is, but exactly, it's kind of hard to wrap your head around that, but 10.5 dozen, now those donuts are, arranged in boxes, and you kind of get like, oh God, that's a lot of boxes of donuts, kind of what this would look like. Or complex has 1476 residents, 10.25 score. If you don't know what a score is, it's not necessarily useful, but all you have to do is learn what a score is, right? 20, and so that lets you kind of work through that. One important aspect of counting units is that you can use them to count anything, right? Dozen is always 12. It doesn't matter what it is that you're counting. You could have we usually use it for like food items, but you could have a dozen buses, you could have a dozen stars, a dozen galaxies, anything like that, and it'll always be 12. So we want to get some kind of work through some problems dealing with counting units because we're going to do some for chemistry, so new ones for chemistry. So let's get some practice on just using counting units in a context we're maybe more familiar with. So a bakery prepares 312 bagels. How many dozens of bagels has the bakery produced? Always want to start by thinking about what do we want. Okay, when reading this out, what kind of units should our answer have? It's going to be dozens of bagels. So how many dozens of bagels? One of the ways we can always pierce that out, remember, is that it's a unit that doesn't have a number next to it. So that's a good sign that that is going to be the answer of our units. Asking what do we have, then lets us look at what numbers are associated with units. And so we can see that this conversion idea is we're going from total bagels. 312 bagels is a count of bagels. And we want to relate that to a dozens of bagels. So a counting by group. Our answer is going to be a number of groups of bagels. And then we want to take that from a total count of bagels. And so we're going to relate those via the definition of the size of those groups, right? How big is 1 dozen? And so that definition of a dozen is always true. It doesn't matter that we're counting bagels. It's always 12. So let's see what this looks like when we work it out. Bakery prepares 312 bagels. How many dozens of bagels has the bakery produced? So we know what we want is how many dozens of bagels, and what we have is 312 bagels. So if we write this out, see that we're starting with, you can see that we're starting with 312 bagels. And we want to go to some dozen of bagels. So our version is going to be then, we know we want to end up in dozen. On the bottom is going to be bagels. If you look there, we can see that the bagels would cancel each other out, the dozen would cancel each other out, and we'd be good to go. So the question is, what is the definition or the conversion between dozens and bagels? And we know this is just based on the definition of a dozen. 1 dozen is 12 bagels. And so we can see that what we're doing is changing from counting individual bagels to counting bagels by group. And so the conversion factor there is going to be a question of how big is your group. It is 12 bagels for every 1 dozen. So we're going to do 312 times 1 divided by 12, which gives me 26 dozen bagels. While we're used to using these counting units to describe things, namely food, we also want to start thinking about how we can apply them to chemistry. And so, if we think about some questions, which of the following contains the largest number of bakery treats? 1 dozen donuts, 1 dozen cinnamon rolls, and 1 dozen eclairs. Got some nice tempting visual aids for us there. And so when we think about this idea, we know that when we look at this definition, 1 dozen means 12. 1 dozen means 12. 1 dozen means 12. And so if all we care about is the number of bakery treats, all of those contain the same amount, 12, 12, 12, So they all contain the same. When we use these sorts of counting units like dozen, it doesn't matter what we are counting, we always have 12 of them. So when we look at something like in a chemical context, the objects of choice are going to be molecules. And so we said for chemical reactions, we care about the number of molecules. And so we can count molecules using counting units. We could say I have 1 dozen C6H6. Here's a picture of that molecule. 1 dozen water. Here's a picture of that molecule. And then 1 dozen O2 molecules. Right? And so in all of these cases, these molecules are different sizes. C6H6 is quite larger than the other two, but it doesn't matter. In all cases, they are still the same. 12, 12, 12 is the number of molecules that we're dealing with. And so when we're looking at these counting units, we can count anything, any object we want, and it'll always have the same definition. 12 molecules is not a lot of molecules. Dozen isn't very useful there, but we could certainly still count in that way.